We're going to start now discussing nutrient cycles. But before I want to clarify that this is part of biogeochemical cycles. However, we have omitted the water cycle in this conversation, which is part of the overall biogeochemical cycles. So we're focusing now in nutrient cycles. But in general, biochemical cycles are the ones that allows the recycling of elements, of chemical elements within ecosystems. And the ways that in which an element or compound is moved between living and non-living organisms are called the biogeochemical cycles. All right. Biogeochemical cycles are important to living organisms and are actually the the bones or the structure of organisms. So these are carbon, nitrogen, phosphorus, and sulfur. And then naturally, the geologic processes such as weathering of rocks, erosion, and other movement of continental plates play a role on recycling the materials and the interactions among organisms. So we have biological interactions, and we also have only merely physical or geological process that are part of the interactions of the biogeochemical elements. So one of these key elements is the carbon. Carbon is essential for the bodies of living organisms, and it is now also economically important because it is the main element on fossil fuels. And then we're going to start discussing also the human influence of the carbon cycle that is directly connected to the use of fossil fuels, but also to deforestation that limits the amount of CO2 that is being taken from the atmosphere. So the major carbon reservoirs are the atmosphere, the fossil fuels, the oceans, and the terrestrial biosphere. If you see on this table, you can see that the major reservoir of carbon is located in the oceans with around 85%. And then we have another major reservoir on fossil fuels, and then terrestrial biosphere, and a small amount in the atmosphere. So how the carbon is being transported within these regions or these sources, we know that the main one is photosynthesis. And before we were talking about primary productivity. So photosynthesis is the process of taking CO2 from the atmosphere by plants and phototrophous organisms, and they convert this CO2 into molecules, right? Organic molecules such as glucose, and other compounds such as sugars, etc. Body tissue in general. And then we also have the process, the inverse process that humans do and animals, right? Which is the respiration process. So from that, we will return the CO2 to the atmosphere. Plants also do this process, but it's in a minor balance as compared to the photosynthesis process. Another way for carbon to enter the atmosphere is by the eruption of volcanoes, and also by entering through hydrothermal vents. There are two main drivers of carbon in the Earth. One is more rapid than the other one, so the geological pathway is very slow, and it takes like even millions of years. And the biological pathways is more dynamic or more rapid. When I'm talking about the geological pathway, is when we have carbon that is sink in the sediment of the ocean floor and also in sediments on the earth, and then over time these sediments turns into limestone, and this is a big carbon reservoir. And this carbon reservoir is actually the one that we have encountered in fossil fuels, that is that are formed due to the decomposition of living organisms, and also that from the weathering of terrestrial rock and minerals, right? So now this figure is actually accounting for the human additions of carbon that are marked in red. And then the other cycles are also indicated, and the numbers that are indicated in the figure are the gigatons of carbon that are moving from one area to another. So since this figure is coming from a book chapter more updated, it has higher values, for instance, for the atmosphere. So now we have 750 gigatons of carbon as compared to the previous table. And then we also have, we can see, what is interesting to see, for instance, is that in plant growth and decay, we always have a surplus of uptake of carbon, right? Because we have a value of 60 that is being released over 121 that is taken. And then we also have the same case for the exchange ocean atmosphere, where we have 92 coming into the ocean while 90 is only going back. So there is a positive input or on the oceans, right? That is being taking carbon. However, this is not enough now anymore due to the human activities. So to put this into perspective, I can say that photosynthesis takes approximately 120 million metric tons per year of carbon. And this is 20 times greater than the annual human CO2 emissions. So for annual human CO2 emissions, I'm just talking about respiration. And so before the Industrial Revolution, carbon on the atmosphere and carbon on the earth was on the land was in balance. So one of the reasons, one of the main drivers, that are the combustion of fossil fuels. This is pumping carbon to the atmosphere all the time. But there is another one process that is been affecting also the carbon cycle a lot, and is the clearing of forest and of land areas, ecosystems, that are the ones that takes all the CO2 from the atmosphere, or takes the majority of the CO2 from the atmosphere. In the figure, we can also see three major cycles that occur in the ocean, moving the carbon, which is the exchange ocean atmosphere, the exchange surface water deep water, and the intermediate and deep water cycle, right? And there are some other small tiny cycle on the surface sediment, and all these ones, all the ones in the ocean, we're going to discuss in detail. And then also what I want to see on the other side, on the land, major cycles are the plant growth and decay, and the land use changes due to this is mainly human activities, right? And then what is important also to mention is that fossil fuel and also cement production are the ones that are pumping or releasing the CO2 into the atmosphere. So let's talk now about the marine carbon cycle. This one starts in the surface, where a carbon dioxide is absorbed, and it is exchanged. This is called fast carbon cycle because it occurs at a more rapid scale as compared to the other ones that we will discuss. This one occurs to the uptake of CO2 from the phytoplankton and microscopic plant-like organisms, and these are the ones that take and that these are the ones actually that pump into the atmosphere 80% of all oxygen that is in the atmosphere. And then once this carbon enters into the oceans, I mean in the form of phytoplankton, then it enters the food webs. So to put this into perspective, an individual whale will take in krill equivalent to 4% of its body weight every day. And their long lifespans mean they are able to keep much of this carbon from returning to the atmosphere. So once this carbon has entered the trophic levels, it goes now into, it can move into deeper waters by the animals, the creatures that live there, that take some of this carbon as well from this food web. They release some of the some of the carbon CO2 to the atmosphere as they respire, but then they start storing this carbon also within their bodies. And then when they die or defecate, the waste products containing carbon are released into the ocean, the open ocean. But in this case, once it goes to deeper waters, unlike respiration, which produces gases, this process don't return the carbon to the atmosphere. So basically, they move it downwards into deeper waters. And a constant shower of organic material and debris falling from the more productive shallow waters, this is called marine snow, goes into deeper waters and enters something that is called the slow carbon cycle. And this slow carbon cycle is the movement of the carbon by detritivores, squids that are in deeper waters, and that it is a little bit slower because the carbon doesn't go back to the atmosphere as CO2. All right. And then we have a bottom layer, the end of the carbon cycle, which is actually one of the most important ones. And is the one that the material that the carbon that goes to sediments, sediment into the floor, ocean floor. And this one is a very important carbon sink because this will create a formation of material that can storage carbon for millions of years. So from the carbon cycle, we can also distinguish the main drivers, or the main is called the pumps, and these are the ones who define the compounds, the carbon compounds within the system, and also the velocity at which these cycles occur. One is called the biological pump, and is the one that we've been discussing, where primary producers or plants take the carbon from the atmosphere, and then it's being consumed and transformed into organic material, right? Then we have something that is called the physical pump, and this pump is the one that drives the transformation of CO2 to bicarbonates or vice versa. And this is driven by the thermohaline circulation, the one that we were discussing about before on ocean circulation. And this one and this is because this one is pH dependent. So the pH is moved due to the saline concentrations and due to temperature as well, right? And this one it also affects the pH and the equilibrium of the CO2, all right? And then we have the carbonate pump, and the carbonate pump is basically the fixation of dissolving organic carbon, the bicarbonates, HCO3, with the available calcium to calcium carbonate, or the sediments or the minerals that are settled in the bottom of the oceans. So if we disrupt one of these pumps, think about the consequences. And this one, one of the disruptions into the oceans is ocean acidification. And imagine if we acidify the oceans, that will mean that the physical pump will no longer operate in the same way, which means that it will not be able to storage the CO2 from the atmosphere that is now there as sink in the ocean. The balance that we were talking about, the 92 being taken by the ocean, and 90 gigatons only emitted.